Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on September 2nd, 2025, about 5 days ago. The standout contribution is a clear path to provable control. It argues that reliable, data-driven feedback requires bilinear Koopman surrogates with quantified proportional residual bounds, which then enable closed-loop guarantees. The paper is titled, An Overview of Koopman-based Control, from Error Bounds to Closed-Loop Guarantees. And, as we will see later, the implications for controller design are quite significant. In short, the survey links finite data approximations, explicit error bounds, and robust synthesis methods to certify stability and performance. On X, a prominent voice highlights rapid progress in Koopman control and praises the survey for laying theoretical guarantees that underpin computations and applications, matching our focus on provable feedback. Engagement looks solid, with about 100 likes. The previous item emphasized guarantees for feedback, and Figure 2 now illustrates the Koopman action on observables. The two 3D surfaces represent a function before and after the operator applies, which means the function is pulled back along system trajectories, so values move according to the dynamics. This mapping acts on functions rather than on states, which is why the geometry of the surface changes while the axes stay the same. The arrow indicates the operator transporting information across time. The previous figure illustrated how the operator transports function values, and Figure 1 now sketches the identity that ties trajectories to observables. Figure 1 shows two pathways. The left follows the ordinary differential equation from an initial state to the state at time t, and then evaluates the observable, while the right applies the operator to the observable first, and then evaluates at the same initial state. The bottom box states these two results are equal, which formalizes pullback of information along trajectories. The previous figure tied trajectories and observables, and Figure 3 now visualizes how approximation error shrinks as the fill distance decreases. The three heat maps compare coarse, medium, and fine sampling, and the color bar shows error dropping from about 10 to the -2 toward 10 to the -6. The transition from red to green indicates sharper, point-wise accuracy, which matters because certified control needs deterministic bounds across the state grid. The previous figure showed error decay with denser sampling, and Figure 4 illustrates why lifted models need careful reprojection. Figure 4 shows the state moving on the bottom plane, while its lifted image evolves on a curved manifold which is not invariant under a simple EDMD step. The blue point marks the surrogate update in lifted space, so a projection back to the manifold and then to the state space is required for consistency. This picture motivates bilinear surrogates with residual bounds, because the miss on that manifold must be quantified. Alright, the previous figure highlighted manifold inconsistency, and Figure 5 presents the full feedback pipeline with guarantees. The left block states the unknown nonlinear system, while the lower path shows data flowing into bilinear EDMD to learn a Koopman-based surrogate. The right block presents the bilinear model with a proportional residual bound, which quantifies model error so robust synthesis can certify a region of attraction. The top right block closes the loop, indicating a controller that achieves certified stability. So the previous figure presented the end-to-end pipeline with guarantees, and this box callout highlights a key open problem. The text states that most certified designs assume full state measurements, which is rarely available in practice. Figure caption text emphasizes input-output data, meaning only inputs and measured outputs are accessible, so guarantees must work without direct state access. Extending robust Koopman control to that setting remains an open challenge that matters for real sensors and actuators. Alright, two takeaways stand out. Reliable data-driven feedback needs bilinear lifted models with proportional residual bounds, and those bounds unlock certified stability and performance through robust synthesis, not just good simulations. The broader implication is practical, provable control from finite data, even for nonlinear plants. That is it for the AI Research Roundup. I am Alex. Thanks for listening.